Hello everyone. According to what we've learned before, we have known that the op-amp plays an important role in the analog circuits, and the MOSFET is another element with important role and wide applications in both analog and digital circuits. Now we introduce the applications of the MOSFET in the digital circuits, which means to use the MOSFET to constitute several basic logic gates such as NOT, NAND, and NOR. The applications of the MOSFET in the analog circuits will be introduced in Lecture 45. Here, the two corresponding symbols of the logic gates in every column have the same meaning. The symbols in row 1 is often used in engineering, while the symbols of the logic gates in row 2 are recommended by IEEE. From now on, you should know their meanings in different places. In previous lecture of the MOSFET circuit model, we have mentioned that when the MOSFET is applied in the digital circuits, its SR model should be applied. In other words, when the MOSFET is turned on, it's equivalent to a resistor between its drain and source terminals. Next, we will analyze how these logic gates realize their designed logic functions with this model. The first one is an inverter formed by the MOSFET. Its function is an inversion, which means when the input is logic 0, the output is logic 1, and when the input is logic 1, the output is logic 0. The 0 and 1 here are logic numbers. We assume 0 represents a signal close to 0 volt, 1 represents to a signal close to 5 volts, and US equals logic 1. You may accept the assumption here that when the input signal UGS equals logic 1 and US equals logic 1, the MOSFET is turned on and operating in the resistive region. Perhaps you may doubt how to ensure that the MOSFET is operating in the resistive region instead of the saturation region. You can analyze this in detail after Lecture 41 about piecewise linear analysis of the nonlinear circuits. You might accept the assumption here as well. Okay, firstly, when UGS is 0, since logic 0 is close to 0 volts, the MOSFET is turned off. The corresponding circuit model is a turned off switch. It's an open circuit between the drain and the source terminals. When UDS equals US equals logic 1, it realizes the function of the inversion, that when the input is 0, the output is 1. Next, when the input signal UGS is logic 1, the MOSFET is turned on, and is equivalent to a resistor between the drain and source terminals. UDS in this condition is the divided voltage of US across R on in this loop. It equals R on over R on plus RL times US. Now the input UGS is logic 1. We hope UDS to be logic 0, which means it's very small value. How to ensure UGS to be logic 0 when UGS is 1 in this expression? Obviously, R on should be far less than RL. In other words, in the digital circuit, the value of RL must be far greater than R on, the on resistance of the MOSFET. Then, the logic function can be realized correctly. You should pay attention to this. Well, let's get the intuitive understanding by simulation about how the inverter formed by the MOSFET realizes the inversion function of the input and output. As shown in the diagram, the input signal UGS of MOSFET 2N7000 is a square wave of 100 Hz. Between the drain and the source terminals is a 5 high level and 100 kilo ohm pull-up resistor. The input signal is represented by the red line. The output signal is represented by the blue line. Click the oscilloscope, open the simulation switch, pause. We can see the input signal is a square wave and the output signal is a good square wave too. Shift the output signal. When the input signal is 0 volt low level, the output signal is 5 volts high level. When the input signal is 5 volts high level, the output signal is 0 volt low level. The logic function of the inverter is verified to be correct. Now we increase the frequency of the input square wave from 100 Hz to 20 kHz. Start the simulation again. Pause. Adjust the time-based scale to be smaller. The output signal is not a square wave with good shape. When the input signal is 5 volt high level, the output is basically 0 volt low level. The logic is correct. However, when the input signal is 0 volt low level, the output is not satisfying 5 volts high level. It means the inverter reaches its maximum operating frequency. When the input signal's frequency is beyond its maximum operating frequency, the result of the logic operation may be wrong. Why does the output of the inverter formed by the MOSFET have a distortion with a high-frequency input signal? We will explain it in detail in the following section of the dynamic circuit. Next, we do an experiment with the inverter compared with the results with those of the theoretical analysis and the simulation to see their differences. This is an inverter formed by the MOSFET. The input signal is a square wave. We can adjust its average value by this adjustable potentiometer. The middle regulating circuit ensures that the input voltage across a gate terminal is a pulse sequence. Use the oscilloscope to observe the input voltage across the gate and the output voltage across the drain. From the waveforms, we can see when the input voltage of the gate is at high level, the output of the drain is at low level. Conversely, when the input voltage of the gate is at low level, the output of the drain is at a high level. The circuit realizes the function of the inverter correctly.